Hello, my name is Zachary Kistler, and welcome to our autonomous vehicle project. Over the course of 3 lab modules, our team took a standard differential drive robot powered by an NVIDIA Jetson Nano and transformed it into a smart vehicle capable of navigating through a miniature city. Today, we're going to walk you through our journey, explain the core mechanics of how our robot thinks and moves, present our navigation plan, and finally, show off a custom demonstration we built. Let's take a look.
My name is Brendan Gilbert, and I'll be summarizing labs 1 through 3. To make our JetBot autonomous, we had to master 5 key learning objectives across 3 labs. In lab 1, we learned basic robot control and kinematics. Because our JetBot doesn't have wheel encoders, we performed odometry calibration by measuring the time and distance traveled at different motor values to estimate our wheel speeds. This allowed us to apply inverse kinematics to plan precise straight lines and turns. In lab 2, we gave the robot eyes. We used image processing techniques to develop a path-following PD controller, allowing the robot to track a yellow line. We also used image recognition to train a deep learning model to recognize traffic signs like stop and speed up. Finally, in lab 3, we put it all together. We established HTTP-based communication between our JetBot and an overhead camera bot. By taking an image of the road, calibrating the camera, and using April tags, we could identify the robot's real-time location. With that data, we performed path planning using a probabilistic roadmap to find the shortest path to a target.
I'm Naim Badru, and I'm going to go through the flowchart for our project. So how do we combine these objectives to navigate from point A to point B? Here is our system flowchart. First, we turn on the JetBot system and initiate our April tag and camera inputs. One of the 2 overhead camera bots take a picture, which the JetBot uses to calculate its current coordinates and heading angle. Next, we input this data into our path planning algorithm to map the shortest route to our destination. Once the path is set, the robot enters a loop. It moves forward using the path following controller. Simultaneously, the front camera runs the traffic sign recognition model. If a sign is detected, the robot decides an action, like reducing speed or stopping for 3 seconds. It then applies kinematics to execute any necessary left or right turns at intersections. Finally, it verifies its location, looping until it successfully reaches the final destination and stops. While our system works well, it has limitations. Currently, we rely on static image for path planning. To improve this design and think outside the box, we could integrate the LiDAR sensor. As noted in our labs, commercial self-driving cars uses a variety of sensors like LiDAR and radar. Adding a 2D LiDAR would allow our JetBot to perform real-time, dynamic obstacle avoidance, rather than just following a pre-planned static map.
I'm Megan Wolf, and I'm going to be going over the demo we did. First, we calculated the required motor values. Using our odometry data, we knew that the motor speed of 0.3 with a bias of -0.017 yields a straight linear speed of roughly 0.5 meters per second. As the robot continues onward, our neural network takes note of its surroundings. We trained our model for 10 epochs using 30 images per category, which were a stop sign, turning, speed limit, and a clear road. When the model detects the stop sign with a high probability, it overrides the motor commands and halts the robot safely. After this process completes, the robot continues onward until the next sign is detected. To demonstrate our mastery of these systems, we designed a custom task that combines the precise kinematics from Lab 1 with the deep learning sign recognition from Lab 2. Our goal was to program the robot to drive forward until it sees a stop sign, then stop for 2 seconds and continue driving onwards.
From manually calculating wheel speeds to training deep learning neural networks, this project taught us exactly how the hardware and software of an autonomous vehicle communicates. By successfully combining kinematics, computer vision, and network mapping, we achieved our goal. Thank you for watching, and please drive safely.